Alrighty. Good morning. Let's get this going. Alrighty. So today, we're gonna start off kind of recapping what we did yesterday by doing some examples using what's called Aze Notation, or just simply an element symbol. How this is gonna work, for example, I'll just give you one right here. An element symbol is going to have 4 parts to it. We're going to have the charge of the element. Remember that charge is protons minus electrons. We're going to have the abbreviation for the element. For example, H is hydrogen. Good morning, Lisa. Or are you saying good morning to Lisa? That's the real question. Down here, we're going to have the atomic number. And let's see, what other colors do I have? Dark blue. And then up here will be the mass number. And remember, that's protons plus neutrons. Atomic number is just number of protons. So, this symbol can basically tell us all the information we need to know about a given particular atom. This is called Aze Notation because it kind of follows this pattern where you have the mass number, which is A, you've got the element symbol, the abbreviation, which is E, and then you have the atomic number Z down there. And so you're going to see that in this particular case, our element is hydrogen. We have a mass number of 2 and a charge of +1. And from all of this information here, we can figure out the number of all of our subatomic particles. So, let me just get rid of this thing so I have more room here. Okay. So, let's see if we can figure out what the number of all of these is going to be. Hopefully, one of them will be easier than the others to do, which would be the protons, right? That's going to be something fixed for every atom of hydrogen, and it's also written there for us in the problem, so we don't even have to think about it. It's got 1 proton. We know that because that is the atomic number of hydrogen, and it's also written there on the bottom left to remind us. If we want to now think about neutrons, we're going to have to use the mass number as our source of information for how many neutrons we have in this particular atom. Knowing that the mass number is given as protons plus neutrons. So we have the mass number 2 there. We know that protons is 1. So therefore, we have 1 neutron in this particular atom. And finally, we have the charge component. It's given to us that the charge is positive 1. If there's a 1, we don't write it, we just say plus. So the charge, which is +1, is equal to protons minus electrons. We have 1 proton, so that tells us we have no electrons in this particular atom. So we can use our element symbol to to try and deduce these informations about the particles. You want to go on the couch, buddy? Here, go over there. Okay. So let's go ahead and do it again. Let's see. How about let's see if we can figure out the number of subatomic particles in this particular ion. So notice that we are missing one piece of information from our element symbol. It's not quite complete, right? We have 2 of our numbers there, but we're missing the last one. However, there is an easy way we can figure out what the last one is. We would just go over to our handy-dandy periodic table. We're going to find phosphorus, which was the symbol P. That's how I know it's phosphorus, but you'll learn those eventually as you go through this. We've got to find it. Aha, here it is. So we have found phosphorus now on our periodic table, and we see that it has the atomic number of 15. So I'm just going to indicate that there to help us remember that phosphorus's atomic number is 15. So with that in mind, note, again, we got this number from the periodic table. So we're able to see that phosphorus is 15. So that tells us that phosphorus has 15 protons. Remember that the identity of your element is dependent on the number of protons. So, moving on to neutrons, we're going to have to use a different number to figure out the number of neutrons. Let's see here. Well, we have the 15 we've already used. Our options are 33 versus the 3 minus. And hopefully we should know to use the 33 to figure out our neutrons there. So 33 is our mass number. That's protons plus neutrons. And so that's going to tell us that we're going to have 33 equals 15 plus our neutrons. So our neutrons will equal 18. Hooray. And then lastly, if we go ahead and look at the electrons here, we're going to base that on the charge. So our charge is -3. That's going to equal protons minus electrons. Protons is 15. Doing all this, we get electrons to be 18 if we solve for that. That's how we would take a symbol and figure out the subatomic particles for it. So I think there's like a table on your worksheet that's going to have you do a bunch of practice with this. So you'll be able to work on that. If we're given the other information, we can figure out what the element symbol is going to be if we're given the number of subatomic particles as well. So let's do that now. Let's say we have protons is 22, neutrons is 26, and electrons is 21. So let's say that's our problem now. Let's try and figure out what's the symbol. Well, so it's really much the same thing that we're doing, but just in reverse that we have been doing. So just like before, the protons are going to be the easier one for us to work with. So let's go ahead and deal with them first. So we know that our element symbol is going to have 4 parts, right? We have atomic number, mass number, the symbol for the element, and then the charge. So if we want to find out the symbol, we're going to have to figure out what element 22 is. We just have to look around here, and lo and behold, there it is. It is titanium. That is going to be our element. So we are going to put Ti as titanium for us. There we have it. We can work on either number next. We've got the mass number and the charge still to do. Let's just do the mass number first. It's protons plus neutrons. This is going to be 22 plus 26, which is 48. Yeah, 48. And then the charge is protons minus electrons, which is going to be 22 minus 21 is positive 1. And so we'll just put a plus in our corner there. All right, so hopefully going backwards is not too bad. So, through this, you should expect to be able to either generate the symbol or generate all of these numbers based on the number of particles or based on the symbol itself. So you'll, of course, always be given enough information to figure these out, but, it's kind of up to you to practice them. So, yeah, exciting. Do we have any questions on that sort of thing? Alrighty. If anything comes up, of course, just throw it in chat. Otherwise, we'll keep on going. Let's talk about elements in nature. That means the natural world, kind of outside the laboratory. Awesome. Okay, so we're going to see that most elements are solids at room temperature. And we're going to see that also with that, that most of them will or can occur both by themselves or in compounds. So, for example, this is silver. You can find it either just as silver metal, or you can find it as various compounds, including silver, like silver oxide, for example. We know that silver is a solid at room temperature. It just is Ag. Fe would be iron. You can find iron by itself. You could find it in compounds like rust or various minerals, or something like silicon. You can kind of find all of these, kind of existing by themselves. However, there are 7 elements that always occur as what are called diatomic, meaning they are made of 2 atoms. And those are going to be hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. If you want to remember these, which you will need to, we're going to see in chemical reactions when we get there, all of these species must be recorded as being diatomic. Anytime you talk about oxygen gas, it's O2. It's not just oxygen. Same thing with any of these elements. A couple ways to memorize these. if we kind of look at where they are on the periodic table, here's my lovely periodic table. These elements there are 7 of them, and they form a 7 on the periodic table. So you've got nitrogen here, oxygen, fluorine, chlorine, bromine, and iodine. Notice that's only 6. The last one, of course, unfortunately, is hydrogen way in its corner over there. But suffice it to say, you've got 7 elements, and they kind of form a 7. One way to do it. Or you can, some people just say Hofbrinkel, or there are other various mnemonics you can use. So Hofbrinkel is the one that I learned way back when, so I still have that in my head. So yeah, there you go. So make sure that you kind of keep that in mind, that these elements always exist as pairs. All right. But we're going to talk more about various groups of things on the periodic table in a little, in the chapter 5 maybe, or possibly chapter 4. I don't remember exactly where it is, but we'll be talking about that kind of later. But just to introduce, some of these elements do come as multiples. Cool. So just throwing that out there. But we can go ahead and move on to compounds. Remember that compounds are more than one element put together. For example, salt is a compound. Water is a compound. Have no fear of ice cold beer. Let's see, does that work? HNFOICB. It kind of works. Yeah. That would be a good way. But just you would have to keep in mind that it is not just C and B, because that would be carbon and boron, but it is in fact chlorine and bromine. So just remember that if you're going to use that mnemonic. It works. Pretty cool. Let's see, what other fun compounds do we have? I don't know. How about glucose? No, 6. What am I doing? Compounds are going to be distinguished in that the ratios between atoms in a compound are fixed. So what this means is that every water molecule has exactly 2 hydrogens and exactly 1 oxygen. So our kind of chemical formulas here tell us exactly how many of that particular atom there are in a given compound. And these ratios are fixed. So every time you see a water molecule, it will have exactly the same atoms in the exact same proportion to every other water molecule. And so we're going to see that this is going to be very useful for us when we're going to be working with mathematics, with compounds, because knowing exactly how many of each atom we have, we can have some fun calculations come out. So we can take advantage of that fact. We're going to see that some compounds will have the same formula as other compounds. And these are called isomers. For example, this is glucose, and this could be fructose, or it could be galactose, or idose, or glucose. There's a bunch of different other sugars that have the same chemical formula as glucose. And these are all going to be isomers of each other, meaning they have the same chemical formula, but their atoms are going to be arranged in different ways. So in chapter 5b, we'll be talking about how atoms get arranged within molecules, and so we'll look more at that. But just throwing them out there here that although compounds would have the same number of atoms and all that, they can be different compounds still. But if we're looking at just a sample of glucose, every single glucose molecule should look the same. So just putting that out there. I think there's some fancy law named for this, like constant composition or something. Whatever, just understand that the ratios are fixed. That's the important part. If you want to put a fun law name to it, go right ahead. Have fun. And also, I think in this chapter there's like a bit of the history of how we know how atoms, or basically evidence we have that atoms look the way we've talked about them. If you want to read that, have fun. I'm not going to test you on some of the experiments people did in like the 1800s to figure out that protons are positively charged. That's not really important to me. More important is that you know that protons are positively charged. They're in the nucleus and they weigh, 1 AMU. So that's what you should focus on, in my opinion. Alrighty. So that being said, we're done with 3A now. So we are going to start 3B, where we're going to be talking about kind of relating individual atoms to more manageable quantities. So atoms are really, really small, right? We can't see them. Their radii are 10 to the minus 10 meters, so they're really, really, really small. And so it's kind of impractical to talk about individual atoms or even hundreds of atoms, just because they're so small that quantities like that just don't really make sense to us, because we can't really it's like talking about 100 bacteria or 100 cells. Like, yeah, you could count that many, but who cares? Like, we have trillions of cells in our bodies. It just doesn't make sense to talk about one cell at a time or hundreds of cells when you have trillions of them going on. And we're going to see with atoms, we're going to have far more than trillions going on. So let's take a look at that. So we're starting chapter 3b now, and we're kind of going to be relating atoms and compounds to real life. We're kind of just quantifying stuff associated with atoms. So we'll get there. Of course, if anyone has any questions, throw them out there as always, but we'll keep on going. So let's start with something that is kind of on your worksheet there, but we'll go through it anyway. So here is our good friend hydrogen. Hydrogen comes in 3 isotopes. There would be hydrogen 1, hydrogen 2, hydrogen 3. And remember, isotopes would have different mass numbers, right? And so, as a result, each of these has its own mass. Right? We would expect the hydrogen 1 to have a mass of 1 AMU, the hydrogen 2 to have a mass of 2 AMU, and hydrogen 3 to have a mass of 3 AMU, right? And we're going to see that because of that, they're all going to have different masses. And so, however, it is kind of tough, to kind of isolate one isotope. And so we're going to basically we're going to apply statistics to this problem of having hydrogen that has all these different masses. We have 3 flavors of hydrogen, each one has its own different mass, and so if we want to be able to relate the mass of a sample of hydrogen to the number of atoms, we can't just say, these 800 atoms, you're all H3, those 2 million atoms, you're H2, and the rest of you are all H1, It's tough to make that call. So we're going to use statistical projections to figure this out. And so I guess I have to write all this stuff. So we use statistics. And this is going to be very useful when we're applying these to large samples. So for example, let's bust open our good friend Wikipedia. Let's show it to you guys. Aha! Okay. I was writing Wikipedia there. Hydrogen. That's what I'm looking up. Blah, 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 blah. Aha! Here is, on all of our fancy Wikipedia pages, they're going to show us the abundance of each isotope in real life. So we can see that most hydrogen, the vast majority of hydrogen, is hydrogen 1, where it does not have any neutrons. And then we have a small amount that is hydrogen 2, and an even smaller amount that's hydrogen 3. Actually, I just realized hydrogen is a pretty crappy example because so much of hydrogen is hydrogen 1. Let's look at a different example here. Let's look at why don't we look at bromine? If we look at the isotopes of bromine that we have about half of bromine is bromine 79, and the other half is bromine 81. Let's keep those numbers in mind for right now. Actually, let's write them down. So if 49% of bromine is bromine 81, and 51% of bromine is bromine 79, we can calculate the average mass of a bromine atom. And we're going to do this by essentially calculating a weighted average. How we're going to do that? The average mass is going to be the mass of the isotope times the abundance. And we would add that to the mass of a different isotope and its abundance. And so on. So bromine only has 2 isotopes, but some elements would have like 7 isotopes. We looked at a couple, maybe platinum has, 5 different isotopes that all exist. But bromine only has 2. You would just add up as many isotopes as you have times their own abundance. So for bromine, we can say that we had the mass number of bromine 79 would be 79. Its abundance was 51%, which is the same thing as 0.51. And we would add that to the other isotope times its abundance. And if we do that, 79 times 0.51 plus 81 times 0.49. What do we get? Oops, I forgot to put... There we go. If we get that, we get, lo and behold, 79.98. Unit for this would be AMU. Since we're using AMU. Creature shush. If we look at our periodic table and click bromine, if we look here, at the very top here, or you might see it on your periodic table just written as is. Notice we have this number 79.9 there. Ours is going to be slightly different because we're using kind of rounded off mass numbers. In real life, we're going to see that, a proton and a neutron do weigh slightly differently. So the mass number is not exactly the same thing as like the real mass, but who cares? That's not really something that we're going to deal with. But we're going to see here that the kind of weighted average for each element is going to be given to us and is calculated that same way where we do a weighted average of all the isotopes. So we can say on average, each bromine atom weighs 79.9 AMU. Oops. So this means on average, each bromine atom. Stop it, Creech. Here, come here. 1 second. See how mad he is? The creature hates everything. Okay, each bromine atom would weigh 79.98 AMU, even though no actual bromine atom weighs 79.98 AMU. We saw bromine can either weigh 79 or 81, but on average, they would weigh 79.98. And we're going to see that this average is going to be very helpful for us because in real life, we just have mixtures of isotopes. We can't really isolate them very easily. Technically we can, but it's extremely expensive and there's really no point to doing it because isotopes would still behave the same way chemically speaking, unless you're looking at very particular applications. And so this is actually going to be something that we're going to finally be able to relate to real life. So let's kind of put that on hold for a second. And let's look at another example. So by the way, this AMU value we calculated is called the atomic mass. So the atomic mass of bromine would be 79.9. In this case, we've calculated it to be 79.98, but depending on whatever your source for the abundance and all that is, yours may be slightly different. We're just going to use whatever the periodic table tells us, so we're not going to really need to calculate these again, but that is where that number comes from. Alrighty. So, long ago, so here's our Star Wars intro. Long ago, scientists decided to base the unit of gram on carbon. So the value of 1 gram, how much do we know 1 gram weighs? They base that off of carbon. So they would be able to say, okay, we can define 1 gram rather than just having some arbitrary unit like the pound or something like that, where a pound is just based on someone had standardized a pound. They're going to base a gram off of carbon, where a certain number of carbon-12 atoms would have a mass of exactly 12 grams. So some way of figuring out how many atoms it would take of carbon-12 to get 12 grams of carbon. So standardizing the gram based on the number of atoms in a sample. Since the number of atoms in a sample is something you can easily, well, not easily, but they can theoretically define for us. So we have some number of carbon-12 atoms is going to be 12 grams. It turns out that this number is abbreviated N sub A, and it is 6.022 times 10 to the 23rd. So it's that many atoms of carbon-12 that will weigh exactly 12 grams. This is called Avogadro's number. And it is how we are going to relate atomic mass units to grams. So atomic mass units are super, super small. You need 10 to the 23rd atoms to even make something in grams. So we can measure grams out. We have scales that do that. A gram, like a teaspoon of water is about 5 grams. So, just even small amounts of grams are somewhat tough for us to visualize. So if you can imagine an AMU, there is no unit for Avogadro's number. We're going to see that it is just a special number. So let's take a moment and look at a few other numbers that we know. Aha. 1 dozen is 12. Notice a dozen doesn't have units either. It would be whatever unit you're putting it with. A dozen eggs, a dozen books, a dozen angry barking dogs, whatever. 12 unit. Whatever it might be. We have another number called a gross, which is 144 of whatever you're looking at. A gross of staplers. I don't know. These are kind of bizarre units, but we just have terms for them. A score is 20 of units. So 407 years ago is 87 years. Right? So a score is 20 of something. We have other words in English. A myriad is 10,000 unit, whatever that may be. 10,000 books. These are all just kind of terms we have. And so we're going to see for us in chemistry. Oh, I see. There's a piece of food just behind the gate here that they're trying to scramble after. That's pretty funny. We're going to have 1 mole for us is going to be just Avogadro's number. So just like a dozen means 12 or a score means 20, we are going to introduce a unit called a mole, which is going to be Avogadro's number for a unit. Before we... All right, let me go figure out how to help this little doggo here. Small one. Come here. Go get that. Okay. I don't know if you guys could hear the scratching on the gate, but that was annoying me, so... COVID teaching at home, woohoo. Our favorite. So, if we were to say... If I had... 3.6 dozen apples. How many apples is that? We can figure it out by using dimensional analysis. We would say, okay, we're going to put 1 dozen on the bottom, and we're going to put 12 apples on top. Those are equal to each other. 1 dozen is equal to 12 of whatever you're counting. We do this. We're probably going to end up with a decimal because who the hell counts 3.6 dozen? Yeah, no, behold, we get 43.2 apples. Whatever, who cares? Well, that's how you do it, right? I mean, if you had 3 dozen eggs, you'd say that's 36 eggs. You would just multiply by 12, right? Nothing crazy there. Notice dozens cancels out. We're left with apples. If we had, I don't know, 9.12 myriad of, what shall we have a lot of? I don't know. Nails. We're working at Home Depot dealing with many, many nails. We can do that. We can bring that into real numbers. We know that we have 10,000 nails for every myriad. And so we have, that many nails. Hooray. Exciting. We have 91,000 nails. Good for us. But that's how you would do those conversions, right? We're going to see that the same thing is going to be applied for all of our atoms and that sort of thing. So, if we go back and we say that Avogadro's number of carbon-12 atoms is 12 grams, we can also say that that is 1 mole of carbon-12 atoms is 12 grams. And so with that, we can see a couple of things. How many carbon-12 atoms are in 82.4 grams of carbon-12? We can figure this out. We know we have 82.4 grams. Just like anything else in chemistry, we're going to be doing a unit conversion. So we do have something that tells us how to go from grams to atoms. And that's that first conversion factor we've put up there. We know for carbon-12, we have 12 grams is Avogadro number of atoms. And doing that, 82.4 divided by 12 times Avogadro's number, we get 4.14 times 10 to the 24 atoms. So we can figure out how many of our atoms, atoms are going to be in a sample for us. This is kind of something we're going to do pretty much only in this chapter because no one talks about atoms like this. It's really absurd to say, okay, let's talk about this 10 to the 24 atoms I have. Instead, we very often will talk about moles instead. It's just an easier unit to deal with. So instead, we can say 82.4 grams times 1 mole over 12 grams. And as we can see here, this is already going to make our calculation easier because we don't have to plug in this number with the crazy exponent. We do that, we get we can just say we have 6.87 moles of carbon. And so that's an easier unit to deal with, right? Nobody wants to write 4.14 times 10 to the 24 atoms when we can just say 6.87 moles. It's just easier, right? And we're going to see that later on, moles are going to be very useful for us when we're talking about figuring out a chemical formula or figuring out how much of a substance is required to react with another substance. We're going to see that moles are going to be the easiest way for us to deal with that. So let's expand our definition. Thankfully, with that carbon-12 nonsense out of the way, we can say that the atomic mass of any atom in grams will equal 1 mole of that atom. I guess I should say element instead of atom, huh? Which tells us that if we go ahead and say that we have 79.9 grams of bromine would be equal to 1 mole of bromine atoms. Or we could also say it's Avogadro's number of bromine atoms. Either one will work. And technically, you can use either one. If you really like Avogadro's number and you love inputting that on your calculator, go right ahead. Stuff will still work with it, but in my opinion, the number 1 is easier to deal with than the number 6.022 times 10 to the 23rd. But that, we're okay with that. So we're going to see that what's called the atomic mass, the atomic mass unit, will be equal to the unit of grams per mole. Mole is abbreviated MOL because why not? Let's just take off one letter and make it shorter somehow. But there it is. We have our moles here. And we're going to see that while we calculated our bromine to have an average mass of 79.9 AMU, that's the same thing as saying 79.9 grams per mole. They are the same unit. So if you go over to your periodic table and you click on, what did we get? Rhodium. We see its atomic mass is given to us already in the units of grams per mole. While some will give AMU, this one in particular gives grams per mole because it's really very important for us to be able to convert between the two. So, if you click on any particular element, you'll get your atomic mass. Or, of course, if you're just using some periodic table, it'll be there on the bottom. So let's actually see here. I think I can, let's pull up a periodic table for us. Okay, here's a periodic table. Let's just make that one bigger. You see these numbers on the bottom here. Oh, what am I doing? Oh, I have the wrong window up. One sec. Let me fix that. Aha. There we go. If we're looking at a periodic table, for example, we can see the atomic mass is given to us at the bottom of the element. Often your atomic number is at the top, your atomic mass is given on the bottom, and the atomic mass is how we're going to relate individual atoms into moles. We're going to see moles is going to be something we're using quite a lot in chemistry. So you can just see all of the various different ones here. Cool. So we're going to see how to use this sort of thing. Let's do another example. How about how much does one atom of lead weigh in grams? You can amaze your friends at your parties by talking about masses of atoms. It's very exciting. Actually, I guess there are no parties. It's COVID. So, oh well. Notice we are just doing a unit conversion. We are going from atoms to grams. That is all we're doing here. And remember, we do have a conversion factor for this. We know that 6.022 times 10 to the 23rd atoms of lead will equal, let's go ahead and find out. Bust out your periodic table. Find lead, there it is. It has an atomic mass of 207.2. we know that that many atoms of lead will equal 207.2 grams. So if we're just finding one atom, we can do that. We always start with what we're given. This is one atom. We're going to put atoms on the bottom so that they cancel out, and we're going to put grams on top. If we want to be very thorough, we'll include our substance as well. Sorry, I've run out of room there. We can do this conversion. We're going to see atoms will cancel out, and we'll be left with grams. So doing that, let's go ahead. 6.022, or rather 1 divided by 6.022 times 10 to the 23rd times 207.2. And so, doing that, we get 3.44 times 10 to the negative 22 grams. So the atom is super duper small, right? We know this. It's completely silly for us to talk about individual atoms because there's no scale that could possibly measure, could weigh out one atom of lead. If you think kind of, most scales or balances that we deal with can measure maybe 0.01 milligrams, 0.001 milligrams. That's just 10 to the minus 5 or 10 to the minus 6 grams. We're at 10 to the minus 22 for a single atom. So we are nowhere near being able to actually weigh something out. And so it really doesn't make any sense for us to talk about individual atoms, but it does make sense for us to talk about moles of atoms. Just because those are actually useful quantities, stuff we can measure out. We can easily measure out 207.2 grams of lead and understand how many atoms we have. Again, this is going to be important for us because we know, for example, that remember atoms in compounds have fixed ratios. For example, hydrogen and oxygen for water. Remember, this tells us we have 2 atoms of hydrogen, 1 atom of oxygen. We can also apply this idea of atomic mass to compounds by adding up the mass of all the elements there. We could see that 1 mole of water molecules would equal the mass of 2 moles of hydrogen plus 1 mole of oxygen. Right? If every water molecule has 2 hydrogens, 1 oxygen, a dozen water molecules would have 2 dozen hydrogens, 1 dozen oxygen. A mole of water molecules would have 2 moles of hydrogen, 1 mole of oxygen. And so we can see that we can add up the atomic masses of these. And we're going to see that this is what's called the molecular mass. Molecules are going to have multiple atoms. We talked about atomic mass when we're looking at individual atoms. We talk about molecular mass when we're dealing with multiple atoms. And we're going to see that is 2 times the atomic mass of hydrogen plus 1 times the atomic mass of oxygen. If we look those up on the periodic table, we would end up getting these. And so we would see that our atomic mass or molecular mass of water would be 18.02. It's the same as just adding up the mass of all the atoms there. Oftentimes, unfortunately, we have many names for molecular mass. We can also call this molecular weight, or formula mass, or formula weight, or more generally, molar mass. This is what I'll probably be using most often. Molar mass is a nice term because it could work for either atoms or compounds. Molar mass is just the mass of 1 mole. So we're going to see that 18.02 grams of water would be 1 mole of water molecules. And that would be made up of 2 moles of hydrogen and 1 mole of oxygen. And so we're going to be able to do the same sort of thing with this. We could say 500 grams of water is how many molecules? We can figure this out. We can go from grams to molecules. Just like we went from grams to atoms or atoms to grams, we could do the same thing by using Avogadro's number. We just calculated that 18.02 grams of water was the same as 1 mole of water. I'm sorry, did I just write grams twice? And so here's another thing you can amaze your friends with. If you take a water bottle that is a half liter, 500 mLs, which are pretty common, you can show them how many molecules of water are in that bottle. So let's start with our 500 grams. And let's go ahead and bust out oddly no, which is just awful. Molecules and moles are completely different things. You can have a mole of molecules. I think the actual word did come from molecules, a way of counting them, but for us, they're completely different quantities in different substances. So for us, they are not related, and don't kind of make that mistake. So let's go ahead and do it. 500 divided by 18.02 times Avogadro's number. What do we get? We get, in this case, so you can go ahead and tell your friends that their water bottle has somewhere along the lines of 10 to the 25th molecules of water. So a water bottle does not have, it's a water bottle. We know what water bottles look like, just the standard, regular water bottle. We're dealing with 10 to the 25 molecules in there. We can easily say, okay, yeah, that's an amount of water that we have in there. We're familiar with that amount. We can measure that amount pretty easily. But again, we cannot measure 10 to the 25th molecules directly. Like, no one's going to sit there counting out, okay, here's one molecule. No. Completely pointless. But we're going to see that understanding this will be very important for when we do chemical reactions. We're going to see that a certain number of molecules would be needed to react to get whatever product we want. And so it'll be important later on. So, a lot of information today. Lots of fun stuff here. Exciting. Very exciting. With that in mind, tomorrow, don't forget, is a review session. So that is purely timed for questions. So on Discord, there is a place for that. Where are we? In this review questions place, as you can see under your tab, go ahead and put stuff there. we so far have 2 questions. So tomorrow I'm only going over 2 questions. Put stuff there. You can put stuff there, anytime from now till when we during the review. Put it during the review. That's fine. I'll go through it in that kind of order. That's something I would suggest doing. I'm glad. So there are practice exams up. There are homework problems. Feel free to put whatever you like there, or just say, hey, can we do another problem going from, calculating the charge of an atom or something, whatever. I'm happy to go over that. So that time is for you. It will be about an hour long, from 9 to 10, just like normal. Though, if we run out of questions, then, we'll just end. Oh, God, I just ate a fly. Cool. Yeah. Anyways, yes. Wash it down. Yikes. What was I saying? Oh, yeah, I guess I'll see you guys tomorrow. I'll also talk about the exam a little bit more tomorrow. I'm sure that will come up as questions. Yeah, isn't that nice? I totally just pepped myself right there. That's lovely. Whatever, free protein. Oh well. Cool. See you guys tomorrow.